This is a $100 bill. It looks like a small piece of paper, but somewhere inside a heavily guarded facility in Fort Worth, Texas, thousands of these are being printed every minute. A single press can produce 32,000 individual bills in 1 hour. By the end of the day, hundreds of millions of dollars may have passed through machines inside this building. But printing the money is not the difficult part. The difficult part is making sure nobody else can, because nearly every inch of this bill has been engineered to expose a fake. The material is not ordinary paper. Security features are buried inside it before printing even begins. The portrait is pressed into the surface using engraved steel plates and enormous force. Some details are too small for most printers to reproduce. Others change color, glow under ultraviolet light, or can only be detected by machines. And running through the center is a blue ribbon filled with microscopic optical structures that took more than a decade to develop. So how does a blank sheet of cotton and linen become one of the most protected objects in the world? It begins before a single drop of ink reaches the surface. Pick up a dollar bill and rub it between your fingers. It feels rougher and stronger than the paper inside a notebook. That is because American banknotes are not made from wood pulp paper. They are made from a mixture of 75% cotton and 25% linen. The result is closer to fabric than ordinary paper, and producing it is a highly controlled process. The material used for United States currency is manufactured specifically for the Bureau of Engraving and Printing. Before the sheets even arrive at the printing facility, the first anti-counterfeiting features are already inside them. Look closely at a genuine bill, and you may notice tiny red and blue fibers scattered throughout the material. They are not small marks printed onto the surface. They are physical fibers mixed into the sheet during manufacturing. A counterfeiter can print red and blue lines onto ordinary paper, but under magnification, the difference becomes clear. Printed marks sit on top. Genuine fibers are buried throughout the material. And that is only the beginning. Hold a $5 bill or anything larger toward a light source, and a thin vertical strip appears inside it. This is the security thread. It is embedded during the manufacturing process and contains the letters USA, along with the denomination of the note. Place that bill beneath ultraviolet light and the thread glows. Each denomination produces a different color. The thread also sits in a different position depending on the bill's value. That prevents one of the simplest counterfeiting techniques, taking a genuine low-value note, removing the ink, and printing a higher denomination over it. The material may still be genuine, but the security thread will reveal the original value. On the $100 bill, however, the most obvious security feature is not hidden from view. It is the blue ribbon running vertically near the center. From a distance, it looks like a strip printed across the surface. But when the note is tilted, tiny images of bells transform into the number 100. Move the bill in another direction, and the images appear to slide from side to side. This movement is not printed animation. It is an optical illusion created by microscopic structures built into the ribbon. The ribbon contains an enormous number of tiny lenses that redirect light depending on the viewing angle. The effect allows an ordinary person to authenticate the bill in seconds without needing any equipment. A printer can reproduce the color blue. A scanner may capture the shapes, but it cannot produce the same moving optical effect on a flat sheet of paper. And the ribbon is not simply glued or printed onto the front. It is woven into the bill's material. By the time these blank sheets arrive at the Bureau of Engraving and Printing, they already contain several layers of security, but they still do not look like money. The first printing stage adds the subtle background colors visible on modern high-denomination notes. Pale shades of blue, orange, and yellow are applied using offset printing. Large rollers transfer ink across both sides of the sheets at high speed, creating the background behind the main portrait and design. These colors may appear decorative, but their real purpose is to complicate reproduction. The soft gradients, fine lines, and overlapping shades are difficult to scan and print without visible changes in color or alignment. But offset printing only creates the foundation. The stage that gives American currency its distinctive appearance and texture uses a much older process, intaglio printing. To understand why it is so difficult to copy, start with the portrait. Benjamin Franklin's face is not simply a photograph placed onto the bill. The image is formed from thousands of engraved lines. An engraver cuts the design into metal in reverse. Shadows are created by placing lines closer together. Lighter areas use wider spacing. Curves in the face, clothing, hair, and eyes must all be built from tiny variations in depth and thickness. One section can contain thousands of separate cuts. The engraver must constantly think backward because everything carved into the plate will appear reversed when printed. A mistake is not as simple as erasing a pencil line. The design is being cut into metal, and Franklin's portrait is only one part of it. Across the note are geometric patterns made from repeating mathematical curves. They twist around the portrait, border the text, and fill areas that may look simple until they are enlarged. Those patterns are designed to break down when reproduced poorly. A low-quality scan may create strange waves. Fine lines may merge together. Small gaps disappear. The counterfeit may look convincing from several feet away, but under magnification, the design begins to collapse. Once the design is transferred onto a printing plate, the sheets move toward the intaglio press. First, thick ink is worked deep into the engraved grooves of the plate. The surface is then wiped almost completely clean, leaving ink only inside the recessed lines. A sheet is placed against the plate and forced into those engravings under tremendous pressure. The material is physically pushed down into the grooves, where it picks up the ink. When the sheet is pulled away, the printed lines sit slightly above the surface. That is why genuine currency has texture. Run your fingernail gently across Franklin's shoulder, the lettering, or the large printed areas. You should feel tiny raised ridges. A normal printer sprays or deposits ink onto a flat surface. It cannot recreate the same compressed material and raised design produced by an industrial intaglio press. The bill is not only designed to be seen, it is designed to be felt. The back of the note is printed first, using green ink. Afterward, the sheets cannot immediately move to the next machine. Intaglio ink is thick and it takes time to dry. The sheets are placed in secure storage for several days. Only after the ink has cured can the front be printed in black. Then they must dry again. At certain moments in the process, enormous amounts of unfinished currency are sitting inside secure vaults. The sheets may already look like money, but they are not yet ready for circulation. They still lack their seals, serial numbers, final security details, and inspection approval. Once the front printing is complete, several features become easier to see. Hold the note toward a light, and a faint image of Benjamin Franklin appears in the blank space beside the portrait. This is the watermark. It is not printed with ink. The image is formed by changing the thickness of the material during manufacturing. Light passes through thinner and thicker sections differently, revealing the portrait from either side of the bill. A counterfeiter can print a pale image onto the surface, but a genuine watermark exists inside the material itself. Then there is the microprinting. Tiny words are hidden around Franklin's collar, near the watermark, and within other areas of the design. To the naked eye, they may resemble ordinary lines. Under magnification, the individual letters become visible. On a genuine note, the characters remain sharp. On a low-quality counterfeit, they often blur together into a dark stripe. Near the bottom of the bill sits a copper-colored inkwell. Inside it is a small Liberty Bell. When the note is tilted, the bell changes from copper to green and appears to fade in and out of the inkwell. The large number 100 in the lower right corner also changes color as the angle shifts. This is created using optically variable ink. The pigment reflects light differently depending on how the bill is held. Ordinary ink may imitate one of the colors, but reproducing the transition between them is much harder. Each feature creates another test. A counterfeiter is not trying to copy one picture. They are trying to reproduce an entire system, and the bill still does not have its identity. At this point, all 32 notes on the same sheet look nearly identical. The next machine changes that. The sheets enter a system known as COPE, Currency Overprinting and Processing Equipment. This is where the Treasury seal, Federal Reserve identifiers, and serial numbers are applied. Every bill receives 2 matching serial numbers on the front. The lettering connects the note to its series and production system, while the digits provide its unique position within that sequence. The numbering process must remain perfectly synchronized across every position on the sheet. A mistake could create duplicated, skipped, or invalid numbers. By the time the sheet leaves this machine, it no longer contains 32 identical designs. It contains 32 individually identified pieces of currency. But nobody simply assumes they are perfect. The sheets are sent through high-speed inspection equipment fitted with cameras and sensors. Both sides of every note are scanned and compared against digital standards. The system looks for smudges, missing ink, incorrect colors, damaged material, alignment problems, folds, and tiny defects that a person might not notice at production speed. Even a small printing error matters. Cash handling machines, banks, retailers, and consumers all depend on the designs being consistent. If one position on the sheet fails inspection, that note is identified and removed from the final count. When a replacement must be printed to preserve the numbering sequence, it can receive a star in place of the final letter in its serial number. These are known as star notes. Most are still worth exactly their face value, although some rare print runs are sought after by collectors. Once the sheets pass inspection, they finally reach the cutting stage. Large stacks are fed into precision guillotine cutters. First, the sheets are cut into strips, then the strips are divided into individual notes. For the first time, the $100 bills exist as separate objects. The notes are counted into stacks of 100 and wrapped with denomination bands. Those stacks are combined into larger bundles, loaded onto pallets, secured, and prepared for shipment into the Federal Reserve System. But the government is not printing new bills simply to flood the economy with more cash. Most production exists to replace notes that are already worn out. Banks return used currency to the Federal Reserve, where machines inspect it at high speed. Bills that remain in good condition are sent back into circulation. Notes that are torn, heavily worn, contaminated, or damaged are removed and destroyed. The $100 bill survives longer than smaller denominations because it is usually handled less often. A $1 bill may pass through countless stores, wallets, vending machines, and cash drawers. A $100 bill is more likely to be stored, saved, or used for occasional large transactions. On average, a $100 note can remain in circulation for more than 2 decades. And despite the machinery, specialized material, security ribbon, engraved printing, inspection systems, and controlled facilities required to produce it, the bill itself costs only a few cents to manufacture. That creates one of the strangest facts about physical money. Almost none of the bill's value comes from the object itself. The cotton, linen, ink, and labor are worth only a fraction of the number printed in the corner. The rest comes from trust. Trust that the bill is genuine. Trust that a bank will accept it. Trust that another person will trade goods or services for it. And trust that the United States government will continue to support its value. That trust extends far beyond America. A large share of all $100 bills circulates or is stored outside the United States. In countries with unstable currencies or high inflation, American banknotes are often used to preserve savings. The $100 bill is portable, widely recognized, and easier to store than large amounts of local currency. That global demand makes it useful. It also makes it a major target. A fake $5 bill offers limited reward. A convincing stack of $100 notes could be worth a fortune. That is why the security system keeps becoming more complicated. Every new feature forces counterfeiters to solve another manufacturing problem. They would need the correct material, then embedded fibers and security threads, then engraved plates and enormous printing pressure, then microscopic lettering, then color-changing ink, then a woven ribbon filled with optical structures, then serial numbers capable of passing bank inspection systems. And even after reproducing all of that, the counterfeit would still need to fool human eyes, human fingers, ultraviolet light, automated bill validators, bank processing equipment, and government inspection machines. From a distance, a $100 bill looks like a small portrait printed onto a rectangle. In reality, it is a compact security system. Nearly every mark has a second purpose. Every material behaves in a particular way. Features that most people will never notice are waiting for someone, or some machine, to challenge the bill's identity. It takes highly controlled materials, microscopic engineering, engraved metal plates, enormous pressure, days of drying, multiple printing stages, and constant inspection to create something most people fold in half and forget inside a wallet. Because the government is not simply printing $100, it is manufacturing something much harder to produce: confidence. Like the video if you enjoyed it, share it with someone who may find it interesting, and subscribe to the channel with notifications enabled to continue learning.